This is the June 22nd, 2023 Physics Regents Part C of the short response, which is the last part of the exam. Okay, question 66. A car initially traveling at a velocity of 25 meters per second west accelerates uniformly at a rate of 1.5 meters per second squared east for 6 seconds. Calculate the magnitude of the car's velocity after 6 seconds. Okay. So we have the initial velocity, we have the acceleration, and we have the time, and we're trying to look for the speed. So we could use VF equals VI plus AT, which means that VF, which we're trying to find, is equal to the initial velocity, which is negative 25 meters per second. And it's negative because it's going west. Negative 25 meters per second plus the acceleration, which is 1.5 meters per second squared east. So it's 1.5 meters per second squared times 6 seconds. And this should give you, let's use a calculator. Now you would get a negative answer, you would get negative 16 meters per second, but since they're asking for the magnitude, we ignore the negative, so it's going to be VF equals 16 meters. Wait, let's write that 16 meters per second. Okay. It would be negative again, but it's asking for the magnitude. Determine the direction of the car's velocity after this 6 seconds. Well, I just said it was negative, so that means it would be going west. Okay. Calculate the total distance traveled by the car during the 6 seconds. Okay. So, what formula could we use? Let's see, go back to a distance formula. So we could use this, or we could use this. I'll use this one. D equals BIT plus 1 half AT squared. Okay. D equals BIT plus 1 half AT squared, which means that D is equal to negative 25 meters. 25 meters per second times a time of 6 seconds plus 1 half acceleration times the time squared. Okay, use your calculator. You would get 123 meters, but round to the whole number, we can just put it as 120 meters. Okay, next. Starting from rest at the top of the slide, a 40-kilogram child accelerates uniformly along the surface of a 4.2-meter long slide at a rate of 0.3 meters per second squared until she reaches the bottom of the slide. Okay, so it's from rest. Accelerates 0.3 meters per second squared until she reaches the bottom. Okay. Calculate the speed of the child the instant she reaches the bottom. Well, we could use BF. Let's see which formula we could use. We could use this formula. Let's use this VF squared equals VI squared plus 2AD, which means that VF, if you take the square root, because we're trying to find the final velocity, take the square root of both sides, VF equals the square root of VI squared. VI squared is just 0, so we could just ignore that. So VF equals the square root of 2 times the acceleration, which is 0. Let's just do the formula first. 2 AD, because VI, the initial velocity, is 0, so just 0 squared would be 0, which is equal to the square root of 2 times 0.3 meters per second squared times the distance of 4.2 meters. Because that's what she traveled right here, 4.2 meters. Which should give you VF equals 1.6 meters per second. Okay, next, calculate the child's kinetic energy at the bottom of the slide. Okay, so the kinetic energy is equal to 1/2 mv squared. The velocity we're going to be using is the one we just calculated right here, because it's asking for the bottom of the slide, and we found the speed for the bottom of the slide. So K equals 1/2 mv squared. So the kinetic energy would be equal to 1/2 of 40 kilograms times the speed, which is 1.6 meters per 1.6 meters per second squared. And this should give you be equal to 51 joules. Okay. Determine the total gravitational potential energy gained by the child when climbing 1.5 meters vertically from the bottom to the top. Okay, yes. So the gravitational potential energy formula is right here. mg delta h. So we could say P E equals mg delta h. Delta just means the change in height, so we're going from 0 to 1.5 meters. So, which means that it's equal to the mass, which is 40 kilograms, times 9.81 meters per second squared, times the change in height, which is from 0 to 1.5 meters. 0.5 meters. Which should give you 5. Let's equal this. 590 joule. Joules. Okay, determine the total amount of mechanical energy. So mechanical energy lost by the child. The child slides from the top. So it would be lost by friction. Okay. So mechanical energy is equal to the addition of the kinetic and the potential. So at its highest point, the kinetic energy is 0 and the gravitational is 590 joules. If we didn't, assuming we didn't lose to friction on the bottom, it would be 590 joules of kinetic energy and 0 joules of gravitational, because we're at the bottom here. Because the mechanical energy is conserved, because the addition of the potential and kinetic at top has to equal to the addition of the kinetic and potential at the bottom. But since we're asking for the mechanical energy lost, the kinetic energy at the bottom is 51 joules, and the gravitational at the top is 590, so they wouldn't be equal. So what you would have to do is get the gravitational potential energy and subtract it by the kinetic energy to determine the mechanical energy lost. So you would just do energy minus kinetic. Wait. Is the kinetic energy, which is equal to 590 joules subtracted with 51 joules. Should give you a rounding to the whole number. It should give you 540 joules. Okay, and that is it for this question. Next question. Okay, for this one I did draw it already because it would have taken a while to get the protractor and do it on the laptop, so I'll just explain this one. So basically, let's start with the question. The diagram below represents a ray of light traveling at that frequency in flame glass incident on air at an angle of incidence of 30 degrees. Calculate the angle of refraction of the light ray in the air. Okay, so what formula you would use? You would use Snell's law, N1 sine theta of the incident angle equals N2 sine theta of the refracted angle. So because you're trying to find the angle of refraction. So then solving for the angle of refraction, you would have to do isolate for sine of theta first, and then you would take the inverse of this, just to show you now, and then to find theta 2, because you have to take the inverse sine, and then you'll be left with theta 2, and then theta 2 would actually equal 56 degrees. You plug in 1.66, which is the index of refraction for flint glass, and then times the incident angle divided by the index of refraction for the second medium, which is air, which is just 1. So then you would just take the inverse then. So then theta 2 would be 56 degrees. And now I just drew it and measured it as 56 degrees. Okay, say what happens to the wavelength, the light ray, as the light ray passes into the air from the flint glass. Okay, so in any instance in refraction, the frequency, so we have this formula, V equals frequency times the wavelength. Velocity equals frequency times the wavelength. The frequency, this is a rule, the frequency will always be the same in refraction. It will not change, because the number of waves per second has no effect with the different medium you're traveling in. The speed will change, but the frequency will remain the same. So the frequency remains the same. The speed will change. So that means that because the index of refraction, we're going into air, the index of refraction is less than flint glass, the speed would be increasing. And if the speed is increasing, the wavelength must increase. Because again, the lower the index of refraction, this is 1, this is 1.66. The lower the index of refraction, the faster it is going to be, the more away from the normal line. So it'll be increases. Okay, the last question of this Regents. Last short response question. A student pulls a block weighing 2 newtons resting on a horizontal laboratory table with a string and force sensor. The sensor measures the force applied to the block when the block is at rest and when the block is moving. The force applied to the block is plotted against time on the graph. Okay. So we have a force sensor, string, a block. So when we pull it, the friction, okay. Based on the graph, determine the force of kinetic friction is pulled at constant velocity. Okay. So right now the force is increasing to start it in motion, so it's static friction, and then once it starts in motion, the kinetic will stay the same right here. So this is the kinetic friction, the one that's staying constant. So it's 0.9 newtons. That's it. Okay, calculate the coefficient of kinetic friction between the block. So, okay, frictional force equals mu. I can't, 1 second. Mu, so let's just do that like that, times force of normal. Okay, which means that we're trying to solve for the coefficient, so mu. We're trying to divide both sides by the normal force divide both sides, and you get the force divided by the normal force will give you the coefficient of friction. So the force is 0.9 newtons. Okay, right? And so let me just fix this. 0.9 0.9 newtons divided by the normal force, which is, it's weighing 2 newtons, so mg is 2 newtons. That's the normal force. So 0.9 newtons divided by 2 newtons. It will give you a coefficient of friction of 0.45. And there is no unit for coefficient of friction because it's a ratio of 2 of the same units. Okay. Question 84. At the instant the block begins to move, what happens to the value? Okay. So we have frictional force. Okay, let's just use this. We have frictional force equals mu times the normal force right here. So it was static, and then it drops and it goes kinetic. So then at the instant it begins to move, what happens to the value of the coefficient? So the normal force will stay the same always, and the force will decrease because it's going down here. The motion is decreasing. So if the frictional force decreases, the coefficient of friction must decrease. So it must decrease. Because the force is decreasing, which means that the coefficient itself is decreasing. That makes sense because the static is increasing, then when it goes kinetic, it drops. How would the coefficient of kinetic friction between the block and the laboratory table be affected if a 0.5 kilogram mass were placed on the block? Okay. Okay, so the coefficient, if you think about it, the coefficient itself would not change. It would stay the same. Because the coefficient, it can't change. It's just it's a property of itself. It can't change. The difference between this question is just saying the coefficient of friction, which is changing from static to kinetic. This is just saying the coefficient of kinetic itself. It will stay the same. It has no relation. It will always stay the same. It's like how the normal force will stay the same if we have just an object. Stay the same. Okay, you know what? Let's just write same. Same. That is it for the physics, June 22nd, 2023 Physics Regents.